Hi everyone. In this video, I am going to continue the scaling factors of the previous video. In the previous video, I have started these scaling models and scaling factors and calculated the scaling factors for 4 different parameters as well. So, we have seen what do you mean by scaling, reducing the sizes of individual parameters of a MOS transistor. So, we have seen there are two parameters like alpha and beta. For all the parameters to get scaled, beta is for thickness of the oxide and voltages, and alpha is for all other remaining parameters. So we have seen the first four parameters like gate area AG, which is scaled by 1 by alpha square, and gate capacitance per unit area C0 is scaled by beta, and gate capacitance EG is scaled by beta by alpha square, whereas the parasitic capacitance we have taken as the fourth parameter Cx is scaled by 1 by alpha. Now the fifth parameter to get scaled is carrier density in channel. Carrier density in channel. Carrier density in channel is Q on. Carrier density in channel is equal to Q on. So that Q on is expressed as Q on is equal to multiplication of capacitance C0 into voltage VGS applied between gate and source terminals. See here Q1 is equal to C0 into VGS. So what do you mean by C0? Already we know C0 is nothing but gate capacitance per unit area, and VGS is the voltage between gate and source. So gate capacitance per unit area. See, you know the individual scaling factors of these two, so that we can get the scaling factor of Q1. We know C0 is scaled by C0 is scaled by, what is the scaling factor of C0? Once go to the calculation, we have calculated already. See here, C0 is scaled by beta. C0 is scaled by beta. So C0 is scaled by beta. And coming to VGS, what is the VGS meaning? VGS is the voltage. Okay, especially we have written voltages are scaled by beta. Okay, VGS is scaled by, therefore it is also scaled by beta, nothing but 1 by beta, and here it is, sorry, C0 is scaled by what? Beta only, not 1 by beta. We have calculated it separately. Okay, so now if you multiply these two, see here Q1 is equal to, therefore Q1 is equal to C0 is scaled by beta and VGS is scaled by 1 by beta. So what is the resultant factor now? Beta beta gets cancelled, and again you will be having C0 into VGS. So there is no scaling factor. Simply with in that case we are saying it is 1. Okay, therefore Q1 has no scaling factor, or we can say Q1 is scaled by unity 1. That means we cannot scale it down. Okay, so now channel resistance. Another one is channel resistance. Channel resistance, that is R on. See here the names may be different, but we know R on is nothing but resistance, on resistance of the transistor. When transistor is said to be in on state, then it is exhibiting some resistance, that is R on. Here it is known as channel resistance. Both are same, you can write that name also. R on is equal to L by W into 1 by Q on into mu. So R on is expressed as L by W Z value into 1 by RS. The sheet resistance can also be expressed in this way, 1 by Q on into mu. Okay, so now if you see this Q on into mu, what is the scaling factor of Q on into mu? Mu is scaled by nothing, because mu cannot be scaled down. Q1 is scaled by 1, just now we have seen previously. and L is L and W are having same scaling factors like alpha. So L is scaled by 1 by alpha and W is scaled by 1 by alpha. So finally, what is the scaling factor of all this? It is unity. Suppose you can also say Rn is equal to Z into Rs. Rn is equal to Z into Rs. That means sheet resistance cannot be scaled down. That is fixed for that sheet. Okay, no scaling. No scaling. In this way also we can understand, because if you don't remember this formula, L by W into 1 by mu on 1 by Q on mu, then you can use this simple formula. Z we know, Z is equal to L by W. So L is scaled by 1 by alpha and beta is scaled by 1 by L omega W. W is also scaled by 1 by alpha. Then R on is having no scaling factor. So we can write R on is scaled by unity. Next, gate delay. Gate delay. So gate delay is indicated by tau d or Td. Gate delay. So gate delay is proportional to, we know tau d is equal to R on into Cg. Okay, we have calculated in the previous video that delay associated with any transistor is equal to multiplication of resistance and capacitance. Coming to this R on is scaled by 1. Just now we have calculated. What about the Cg? Cg is scaled by Cg, gate capacitance. Cg is scaled by, we have already calculated this. What is the Cg scaling factor? Go back. Cg scaling factor, Cg is scaled by this one. Cg is scaled by beta. Sorry, this is this one. See, this C not only. See, Cg is scaled by beta by alpha square. Beta by alpha square. So take the same beta by alpha square. So if you multiply these two, 1 into beta by alpha square, so tau d is also scaled by beta by alpha square. Therefore, Td or tau d is scaled by beta by alpha square. This is the scaling factor of this particular Td. Now, maximum operating frequency F0. Maximum operating frequency F0. We know F0 and time delay both are inversely related. So F0 is equal to, we can write it as F0 is equal to 1 by Td. So the same, the scaling factor, just it got reversed. Therefore, F0 is scaled by alpha square by beta. F0 is scaled by alpha square by beta. Coming to the ninth one, saturation current. Saturation current IDSS. Generally, the drain to source current is represented by IDS. So when the transistor is said to be in saturation, IDS is just replaced by IDSS. Okay, so take this IDSS formula, that is equal to, in terms of C0 W mu by L, which is in saturation. So 2 times here VGS minus VT whole square. VGS minus VT whole square. Now see the individual scaling factors. VGS and VT are scaled by 1 by beta, that we know. As they are voltages, VGS is scaled by 1 by beta. VT is scaled by 1 by beta. And coming to this C0, C0 is scaled by beta, that we have calculated in the previous calculations, and length is scaled by 1 by alpha, and W is scaled by 1 by alpha. So 1 by alpha, 1 by alpha, W by L, that is cancelled, and here 1 by beta will come, and again the VT also 1 by beta will come. If you take out 1 by beta square is the scaling factor for this VGS minus VT whole square, and C0 is having beta, and here it is 1 by beta square. So 1 by beta is the ultimate final IDSS scaling factor. Okay, therefore IDSS is scaled by 1 by beta. Next, current density. Current density indicated by J. Current density indicated by J. Current density, what do you mean by current density? Current density is equal to, is defined as current per unit area. Current per unit area, we can write it as current per unit area. That is what the density mean. That is equal to, what is the current? IDSS by area. Okay, IDSS is scaled by, we know just now calculated, IDSS is scaled by 1 by beta, and A is scaled by 1 by alpha square, because we no need to calculate always A, because A is nothing but multiplication of length and width. Length is scaled by 1 by alpha, width is scaled by 1 by alpha, so it is 1 by alpha square always. Therefore, what about the J? J is scaled by, if you have any doubt you can substitute them, otherwise you can directly write. So IDSS is scaled by 1 by beta, and A is scaled by 1 by alpha square, so they are reversed, alpha square by beta. Therefore, the scaling factor of the current density J is nothing but alpha square by beta. Coming to the next one, switching energy per gate. Switching energy per gate. Switching energy per gate is easy. EG. So EG can be expressed as CG into VDD square by 2. CG into VDD square by 2. So already we know CG is scaled by, what is the CG scaling factor? We have taken previously, CG is scaled by beta by alpha square. So CG is scaled by beta by alpha square, and VDD, as it is a voltage, it must be scaled by beta. So beta square will come, so 1 by, therefore EG is scaled by, so see here, CG is nothing but beta by alpha square into, it is beta, 1 by beta, it is 1 by beta, VDD is scaled by 1 by beta. If you will write here, that is better, that is equal to CG is scaled by beta by alpha square into VDD scaled by 1 by beta, but as it is having square, it is VDD square like this, and divided by, normally you are having 2. So if you take the same value as it is, CG VDD square by 2. What is the factor that additionally we have? Beta will be in the denominator, alpha square beta. This is what the scaling factor. Therefore, Eg is scaled by 1 by alpha square beta. 1 by alpha square beta. Okay. Next, coming to the next parameter, power dissipation per gate. Power dissipation per gate. Power dissipation per gate is indicated by Pg. Okay. See, if you observe clearly, power dissipation per gate Pg consisting of two more parameters, Pg can be expressed as Pgs plus Pgd. Pgs plus Pgd. That means power dissipation per gate to source and power dissipation from gate to drain. So Pgs is having an expression like VDD square by R on. As R on is unity, so PGS VDD scaled by 1 by beta square. So therefore PGS is scaled by 1 by beta square, and similarly PGD is equal to, it is expressed as Eg into F naught. Eg is scaled by, what is the scaling factor of the PGD now? PGD is scaled by, now what is the Eg scaling factor? Eg scaling factor is 1 by alpha square beta, and F naught is scaled by alpha square beta. So alpha square cancel, again it becomes 1 by beta square. See, all these parameters just now we have calculated. If you have any doubt, you can substitute them. Eg is nothing but it is scaled by 1 by alpha square beta. It is scaled by 1 by beta. So if you multiply these two, F naught is scaled by alpha square by beta. So if you multiply these two, that results 1 by beta square. Now see here, PGS is scaled by 1 by beta square, PGD is scaled by 1 by beta square. So what is the scaling factor of PG? Therefore PG is scaled by 1 by beta square. PG is scaled by 1 by beta square. There is a common scaling factor. Coming to the next one, power dissipation per unit gate area. Power dissipation per unit gate. Power dissipation per unit gate area. So we are writing it as PA. Therefore, PA, we know that power dissipation per gate area, PG by AG. PG by AG. What is the scaling factor of PG? Just now we have calculated, that is beta. PG is scaled by 1 by beta square, and AG is scaled by 1 by alpha square. That implies PA is scaled by 1 by beta square by 1 by alpha square. This is alpha square by beta square. Alpha square by beta square. Okay. So the last parameter, that is power speed product. Power speed product. Power speed product, that is indicated by P suffix capital T. P suffix capital T. So PT is equal to power and multiplied by time delay TD. Now we know the individual scaling factors. PG is scaled by 1 by beta square, and TD is scaled by beta by alpha square. Therefore PT is scaled by Pt is scaled by 1 by alpha square beta. So these are the different scaling factors for a MOS transistor circuitry. These are the different scaling factors at each and every stage. But of course we are reducing the sizes. We are reducing the sizes like this. That is fine. But how long it is okay? How long it is fine? Okay, we cannot scale each and every parameter like this, like anyway. Suppose for example, I will tell you one thing. For example, I am taking the parameter length. Length is scaled by alpha. Length is scaled by alpha. Okay, but alpha, as alpha increases, the length becomes very less. What do you mean by length? If you take the transistor diagram, length refers to the distance between source and drain. This is the source terminal and this is the drain terminal. What is the purpose of this distance between the source and drain? That is the distance where the electron can move from here to here. Electron moves from source to drain so that the current will be produced from drain to source. Electron must have a sufficient place to move from source to drain. Okay, unfortunately it is the distance that is shown by L. If L is reducing by number of times by a factor alpha, there exists no gap between the source and drains for the electron to move. And another problem is, it is when a p-type and n-type are connected together, there exists a depletion layer between them. Okay, definitely there should be a minimum gap between these two. That means to avoid the depletion regions to recombine. Okay, suppose n-type region is here, and this is the depletion region. Suppose if you are reducing the length L value, what happens? This depletion region, there is a chance of meeting together. Okay, so the value of choosing L should not make this to happen. If it happens, then the transistor will not work properly. Okay, definitely there should be some limitation at this length of the channel. Similarly, not only length, here I am explaining for example, but not only length, all other parameters are having various limitations, so that the scaling could not be done more beyond that. Okay, that is our next topic. I will explain in the next video what are the different scaling limitations of scaling, and what are their maximum limits. Okay, thank you.